sea of other people were like leaving while I was like getting dressed up. And then like my neighbor came over like,
Oh, John saw the picture. It's how you die in a fire. It's literally how you die in a fire.
you're just sitting there like it's done, and then you realize you can't leave.
In the street.
They were like, they went on until like you got back. The first one had a picture. This was, I assume, like upstairs or something.
I could have made like a ladder out of that sheet.
It's literally how you die in a fire.
Like Kayla, if the building is on fire,
Literally close mountains
fire
country.
on the side of it with bed sheets, your bed sheets are gonna catch on fire and fall.
Yeah, you go for it.
At that point, I feel like I could have.
What day is it?
Live back in the time,
Yeah.
keep moving that statue.
Sorry, what is the date?
I'll listen to your class.
That's 9/9.
I wish I had been around for that. Well, like, yes.
She looks like a 4-year-old. She graduated. You can already see the hair.
I feel like children are nice until, well, my brothers were nice until they hit 6. So they're trying to do that.
Alright, happy Friday guys. Before we actually get started, just a couple quick things. Today's the first office hours, so if any of you have any questions, feel free to swing by office 125 over in the main building. Tutor office hours, it looks like most of you got the email and have responded to the scheduling doodle with your preferred hours to meet with Liam. At this point, the two favorite times are Tuesday and Thursday from 10:30 to 12. However, there were 1 or 2 people that couldn't make it to either of those times. So there's also a possibility of adding Tuesday at 6 p.m. If you feel strongly about any of those times and you have not yet responded to the doodle, do so that I can take into account your schedule when I set up a time for Liam to be in the conference room. Alright, also, there was a question about this last time. All of these lecture slides are uploaded to the Canvas site, if you haven't seen that yet. So I'll try to upload them. This one I didn't get uploaded till this morning, but I'll try to upload them the night before so that if you feel like it, you can print them out, take notes on them, what have you. There are also recordings of these lectures linked through the Canvas site, so if you go on there, go to lecture recordings, you can see each of the lectures as a video with screen capture slides, so you can see whatever's up here. And last item, I put an announcement up, but just in case you guys feel very strongly that you do or do not like certain styles of my lectures, there's a anonymous feedback forum on the Canvas site. You can think of it as your anonymous Dropbox for hate mail or questions. If there's something that I didn't get to in lecture, or something that I did that you'd like to see in future lectures as a strategy, just drop a note in there and I'll try to work them in as we go through the semester. Alright, so today, lecture 2. This is wrapping up chapter 1 of the book. So the topics today are going to be scalars, vectors, tensors, viscosity, and stress tensor. Newtonian and non-Newtonian fluids. And surface tension. And then at the end, there was a question already through the website feedback that it seems like maybe the idea of the continuum hypothesis was still a little murky for some folks. So we'll, if we have time, we'll revisit the continuum hypothesis. Okay, so I wrapped up last lecture with this example video that shows two fluids with identical densities, right? Fresh water, silicone oil. However, one of them clearly is a lot more reluctant to move or pour. You know, it's got this very sludge-like behavior. And so what we're going to cover today is the math behind and the physics behind why certain fluids behave in this very slow fashion. So to begin with, scalars, vectors, and tensors. You're probably all familiar with scalars and vectors to varying levels of comfort from physics classes. But tensors, as a general thing, may or may not be something we've dealt with before. So scalars, obviously, contain only information about the magnitude of something. Vectors contain magnitude and direction. It's this big and it's pointing this way. So examples of scalar might be a density or a pressure, something where you only need one number to describe it. Vectors, you need both, you need an arbitrary number of numbers, but you need the magnitude and the direction in which the arrow is actually pointing. Examples being the position, x, y, z, might be elements of your position vector, or velocity, u, v, w, may be elements of your velocity vector. Tensors are values that include any combination of magnitude, direction, and orientation. So this may mean this means that you need two elements or more to describe, or you need two indices or more to describe the element of a tensor. So, for example, I put this at the bottom. The scalar value, if I say how many students are in the class, the answer would hopefully be 19. The vector may be how many students seated at each table. So, I could say n students, 19. That's the only number I need. Now, the number of students per table, well, we'll say n ij would equal 4 tables 1, 2, 3, 4, 5. So we've got I equals 1, 2, 3, 4, 5. We've got Joe at this table, 1, 2, 3, 4, 4 at this table, 1, 2, 3, 4, 5, 7 at that table, 4 and 2. So that means if I ask for the number of students at each table, let's say ni, sorry, you're going to get an element that is the number of tables long and contains a value for the number of students in each table. If I ask for a tensor value, the example might be the number of students at each table that are asleep or awake. If I assign a value of 1 to mean awake, a value of 0 to mean asleep, then I could further divide each of these numbers into two numbers that represent the number of sleeping and waking students. You might be more familiar with these in the form of a vector, or sorry, of a matrix. A matrix, unlike a vector, has two dimensions, right? The only difference between a matrix and a tensor is that tensors have an arbitrary number of dimensions. You can have, for example, in solid mechanics, when you're applying Hooke's law to the extensibility of a solid, you would use a tensor called the compliance tensor, which is C, I, J, K, L. It's a four-dimensional tensor, right, or fourth-order tensor. So we're going to spend a little bit of time on the tensor topic because this is again, it's a hard one to kind of to get across in words only. So tensors are described by their order. Think of a tensor as just an array, right? It's a collection of numbers. They're described by their order, and the order is the number of indices you need to pick out an element. So if it's a four-dimensional array, right, C, I, J, K, L, It's a fourth order tensor. That means if you want a single number from inside that tensor, you need to specify a value of I, a value of j, a value of k, a value of l. So scalars and vectors are just actually special names we give to 0th order and 1st order tensors. Matrices would then, because they have two indices, be 2nd order tensors. Alright. I don't think in this course we go beyond 2nd order tensors, so I don't think you're going to see anything bigger with higher dimensional than a matrix. But don't hold me to that. Something else might pop up. We'll get to some examples of tensors in upcoming slides, and feel free to, let's see. Yep. All right, so in fluid mechanics, the most important tensor, or matrix, is what we call the stress tensor. So we're going to derive the stress tensor now, and actually I'm going to do it up here so that it shows up better for everyone. Okay, so let's first draw a three-dimensional space. X, Y, and Z. And then let's assume we take a small little area in the space with a normal pointing along the x-axis, right? We're going to call this little area delta A. I'm going to be using this delta notation here a lot, and this really just means a very small quantity of something. So this is a very small little elemental area, okay, and it's at a constant x. Now we can apply a couple forces to this small little area. We'll put this one here, which we call delta Fx. We'll put one in the y direction, which we call delta Fy. And we can put one in the z direction, which we call delta Fz. Okay, now what is the, how do you compute stress? Alright, what are the quantities we put into stress? Anyone? Euler. No, alright. Stress is just force divided by an area. Okay? Same units as pressure, but that's what you get. So force divided by area. In this case, our forces are dFx, dFy, dFz. And our area is dA, sorry, I meant to subscript this by x. The subscript on the area just means that the normal vector points in the x direction. So we're going to define three stresses. The first is what we call tau xx. We also call this sigma xx is equal to dfx divided by dax. Next one is what we call tau xy, and this is equal to dfy divided by dfx. Last one is tau xz. dfz, it's supposed to be ax. Alright, let me color code these so it's clear which ones are which. Alright, the idea here is that if you divide each of these respective forces by this area with a normal in the x direction, you get these three stress components. This one here is what we call this normal stress. And these are shear stresses. Have you guys taken any solid mechanics courses at this point? Mechanics Electronics, materials, stuff. Okay, so you've come across, I'm sure, at some point, normal and shear stresses. Now, if you notice the subscripting here, the x stays constant here. That's because the first subscript on this tau is equal to the subscript of the area, the elemental area that we're using to divide the force by, and the second subscript is the direction in which the force is pointing. And this is the general rule of thumb when we're denoting stresses. Okay? Tau ij means force in direction j over area with normal I. So if we instead want to write out, let's get rid of these forces here. That means we can represent these three little these three vectors, right, in this 3D space as stresses instead of forces. So we have tau x y, sigma x x, and tau x z. So let's take this up a notch and go with, instead of just a little area, we're going to draw there go my fantastic artistic skills again. Okay. X, Y, Z. So now in this case, we have, instead of just an area, a cube. I know it's not a very good cube, but bear with me. Let's pretend it's a cube. So this face here has a normal and along the x-axis. This face has a normal along the z-axis, and this face has a normal along the y-axis. So following the same reasoning, we can draw out a 3-element stress vector on each of these faces. And so okay, so if this face here is x, what would be the subscript of, somebody, what would be the subscript of this, I'll draw these one at a time, of this stress, right here. Remember, tau. Alright, use this formula here. What's going to be, how do I denote this stress here? Force in this direction, face with a constant x value. Or, anyone? Yeah?
Tau x, or tau I.
Tau I. Yeah, that's the right idea. Tau xx, though, we're going to use the actual coordinate directions, right? But, exactly. So, tau xx, which we also call, as I said, sigma xx. When they have the same subscripts, that means the force is perpendicular to the face, and therefore it's creating a normal stress, sigma. Alright. Now this one, also, same face, but now pointing in the y direction. Someone. Tau xy, exactly. So this one's going to be tau xz. Alright. This one, top face here. Somebody. Okay, normal is pointing in along the y-axis, the force is pointing along the y-axis, which gives us y, or sigma yy. Good. This one, face has constant y, force in the z direction. That was it. And this one, tau y x. All right, last face here. Tau z equals sigma cz. And tau cy. There's a little whisper here. Okay. So this is our drawings of shear stress on a small little cube, a cubic volume in a fluid. Right? Now bear in mind this is supposed to be a really tiny little cube, such that we can consider it almost a point in space. So the things to note here are arrows that are pointing towards the same edge here have the same subscripts, but they're reversed. Okay? And we'll get to why that is in a moment. Forces normal to their own face, create a normal stress, so on and so forth. You get it. So if we write this in a tensor form, this means that our tau tensor, we denote tensors with a double underline, is going to be equal to sigma x x, tau x y, tau x z, tau y x, sigma y y, tau y z, tau z x, tau z y, sigma z z. So again, like I said, this is a second order tensor, which is more familiarly known as a matrix. Each column here denotes the direction that the force is aimed, and each row correlates to a face on this cube. Now, let's see if we get to this yet. Not quite. All right, the other thing to note on here is the convention we use for the signs on stresses. So, as a rule of thumb, the sign is positive when the stress and the normal of the face point in the same direction. Right? So, by pointing in opposite directions, that means it's a negative stress. So, let me okay. So, this element here, if this is x, y, z, is going to be tau y, y equals sigma y, y, and is it positive or negative? Positive. This one here is tau x z. Is it positive or negative? Anybody? Negative. Good. All right, you get the idea. Okay. Now, we don't get to this quite yet, but if you imagine that we take this cube to be, as I said, vanishingly small, to where it approaches being a point in space, where it's essentially a tiny little particle. If it gets down to the size of a molecule, you know, then it's going to, for all intents and purposes, move as a rigid body. So it's not going to deform, which means x we'll just do this in a 2D sense. You know what? Okay. Sorry guys, forget about this for right now. We'll be getting into this when we hit the differential analysis of fluid flow. But I'll tell you now that this tensor here is symmetric. That means tau yx equals tau xy. They're equivalent in magnitude. They're just in different directions. And as I said, we'll get into that when we start looking at the equations of motion for one of these little cubes. But that's not quite yet. Alright, so we just derived the form of the stress tensor. As I said, this is a little cube taken out of a volume of fluid. In this image, you'll notice that the coordinate directions are a little bit different, but the sign convention remains the same. Alright. So, remember the constitutive relation for fluids is that the stress is a function of the rate of strain, okay? As opposed to solids where it's a function of just the strain. So let's examine, now that we've developed this side of the equation, we've learned about the stress tensor and how to describe that, let's look a little bit more closely at the other parts of this relationship. So let's consider my black marker. So let's consider tau xy, right slope for tau. So I'm going to recreate this drawing on the board. We've got two plates with fluid between them. We'll assume this plate stays fixed, and this plate will have a force applied to it. We'll call it F. We're going to define a couple of points on these plates. As I do in the image, this will be A, B, C, and D. The idea being we should be able to draw a straight line from A to B and a straight vertical line from C to D. So this is before the plate starts moving. Now we apply this force, and we're going to see that the plate slides along the fluid. Now sometime later, we'll say this is dfx for the sake of argument, x, y. So at time equals 0, this is before anything has started moving. Okay. Now at, let's say time equals some small instant later, everything here will have shifted over to the right. That constant amount. dx. Alright, now we're assuming that this thing is moving at a constant velocity because the force has been, there's a constant force applied. So if this is moving at a velocity now of delta u, then delta x is just going to be equal to delta u times delta t, right? X equals velocity times time. That means that each of these arcs from the original line connecting A to B to the new line connecting A to B forms an angle angle delta beta. And also note that because this plate moves along as a rigid body, dx here is equal to dx here. Or delta x. Okay. So let's call this delta beta. Figure out where to write. Let's turn this off for a second. Put it up here. Okay. Delta beta is equal to the arctangent of delta x over delta y. And this distance between the plates we're calling delta y. Now, we're going to call this our deformation of the fluid. Which means that the rate of deformation is equal to the limit as delta t approaches 0 of delta beta over delta t, which is just equal to the derivative beta with respect to t. Now, because with the limit of delta t approaching 0, delta beta becomes extremely small, right? And the small angle approximation, you guys know the small angle approximation. If the value outside or inside of a tangent, right? If the limit as x approaches 0 of tangent x equals x, right? This is a very useful approximation, and we can apply it now to this, because as delta t approaches 0, delta beta will also approach 0. And so delta beta will be approximately equal to delta x over delta y. So if we plug this into here, then we can get that limit as delta t approaches 0 of delta beta over delta t is equal to the limit as delta t approaches 0 of delta u delta y times delta t times delta t. Right? Delta x is equal to delta u times delta t. Delta y carries over, and we carry over this delta t here. So this means that the derivative of beta with respect to time is equal to du over dy. And this is what we call our strain rate, or the rate of fluid deformation between two moving plates. Now, we may, in other words, if we draw all of our little velocities in the fluid as these arrows, then what this tells us is that the rate of increase with velocity as you move away from this point is the strain rate, du dy. need another minute to write any of this down. Let me let the projector warm back up. It's upset. Okay. And, well, while the projector's waking up. So, when we say that, there we go. So if we rewrite the constitutive equation for a fluid now, tau xy is equal to a function now of the rate of strain, which we have defined as du dy. And most importantly is we're going to uncover what this function is. Remember I mentioned that a constitutive equation is empirical. People figure it out through experiments. They do a bunch, they say, oh, it behaves in some fashion using dimensional analysis. And what they figured out is that tau xy is equal to a variable called mu times du dy. So it's a linear function. There we go. It's a linear function of the rate of strain in a fluid. And this applies for a broad class of fluids that we call Newtonian. Let me scratch off the things we've covered. So, covered that. We got through. Yeah. So, as I mentioned, tau. Bad me, I got the stress tensor backwards. Tau yx. Yx. Okay. So we've uncovered the form of this function through experiments. This isn't some magic mathematical trickery that gives you this function. This is good old putting fluids between plates, dragging them, measuring the force, measuring the velocity distribution between the plates, and saying, hey, this function does a pretty good job for most fluids. And as I said, fluids that obey this law we call Newtonian. So mu is what we call this constant of proportionality, and we call it the dynamic or absolute viscosity. So quickly, we're going to do a little bit of a recall from the last lecture. Let me rewrite this at the top of the board. Tau yx is equal to mu times du dy. All right, now we're going to figure out what are the dimensions of mu. Remember, dimensions are mass, length, time, temperature. I sure hope we don't need that one. And all right, so first, let's tackle this in chunks. Stress, set force over area. So somebody's going to give me the dimensions of that. Remember, same as pressure. Anybody want to volunteer? Force over area. All right, let's start out smaller. Area.
L squared. L squared.
Good. Force is equal to mass times acceleration, right? So L
Squared.
T
Squared.
squared, or, well, negatives, yeah, to the negative 2. Right. So mass, like -1 times -2. Okay. And it's easier on the tablet, we can just drag this over here. So, mass, length, -1 times -2. Alright. du dy. Remember, taking a derivative does not, each of these maintains its dimensions. Du just means really vanishingly small u, dy is really vanishingly small y. So u is a velocity, so it has dimensions of what? L over t, good. L, t to the negative 1. Y is just distance, so it's length, right? So this leaves us with time to the negative 1. Alright, so if we're going to solve for the dimensions of mu, we're just going to move this time over here, right? So let's say time negative 1. Which gives us what? Mass, length negative 1, time negative 1, yeah. Cool. So these are the dimensions of mu, or our dynamic viscosity. There's another form of viscosity. Oops. Oh no. Take that over to me. Alright, there's another form of viscosity that we'll use sometimes, which we denote nu. So there's mu and there's nu. We're going to start getting into some heavy-duty Greek letters, by the way, if you haven't noticed already. And this is just defined as mu divided by density. Okay, this comes into play later, but just so you know, it's coming 2 measures of viscosity. They're related by the density of the fluid. So, here we go. All right. So, as I mentioned, Newtonian fluids are those which have this linear relationship between shear stress and this du dy. So water, hot water, air, crude oil. The idea is, as you shear it faster, if you move the upper plate in that diagram faster and faster, then the rate of, or then the shear stress is going to increase linearly with that. Non-Newtonian fluids are those which have a non-linear relationship between shear stress and rate of strain. Shear thickening are those which get harder to shear the faster you shear them. Shear thinning are those that get easier to shear the faster you shear them. And then we have the special kind called Bingham plastics. Think of like toothpaste, for example. Right? If you take toothpaste and you push on it very lightly, you have a blob of toothpaste, and you apply a slight shear force to it, it's not going to just instantly smear. It resists as if it's a solid up to a certain point. Mayonnaise is another example that's used sometimes, right? Once it passes this critical shear stress, then it starts to begin as a fluid, but it behaves as a solid up until that point. So there's another way of looking at this. Let's say, for example, we have a wall. And somebody splatters some liquid drops onto this wall. Now, each of these droplets is going to have a force wrought on it by its own weight, right? And if we went through the trouble of drawing a free body diagram of each of these drops, which we may as well do, if this is a drop, weight, then if it's to remain static, right, at the first instant in time, before if it's not moving at all, then so the y equals 0, which is going to be equal to some force exerted by the wall itself here, which divided by the area of the drop is going to give shear stress. So it's going to be Fy minus W equals 0. And then Fy divided by the, the area of the contact between this drop is going to give you some tau xy. So this drop now has a shearing force applied to it. Okay? Or it's applying a shear stress against the wall. And so if it's a Newtonian fluid, what's going to happen is it's going to start to run down the wall. If it's a Bingham plastic, if this is a blob of toothpaste, you might expect it to stay put. So, Newtonian. If it's a Bingham plastic, as I said, it'll stay put and not move. If it's a shear thickening fluid, it's going to begin to deform and flow down the wall, but it's going to hit it's sort of going to hit its terminal velocity, so to speak, at some point dictated by this curve. Same with the shear thinning. So, an example in this video is going to play now. Alright. So an example from the guys that wrote the textbook is a mixture of cornstarch and water. So you set this blob of cornstarch and water mixed together on a table, and under its own weight, it's going to begin to, behave as if it's a Newtonian fluid. It's flowing smoothly. However, if you begin to try to deform it quickly by pushing it around with a spoon, it's going to exhibit a very solid-like material, or a very solid-like behavior, or in this case, shear thickening. It gets harder to move the harder you push on it. Okay. Another example that I use in my work, and this kind of harkens back to our discussion of streamlines, streak lines, path lines, etc. What you're looking at here is one side of a hydrofoil, right? It's a vertical hydrofoil. You can think of it as similar to a rudder. And I mixed up this paint, and I put this dot matrix of paint dots on the surface of the foil. So the first thing you can observe is that because these aren't all just running down the foil under their own weight, it's a non-Newtonian fluid. It is either a Bingham plastic or a really strongly shear thickening fluid, so that they are flowing very slowly. And the idea here is, that if I put this thing in the water and I begin moving it forward through the water, this is going to pause in just a moment. Alright, so the hydrofoil is moving this direction. There's a camera following it along. Notice these paint dots, as the water flows past them, have not yet begun to really move. They haven't deformed. So the water, as it flows past them, is exerting a shear stress on the paint dots. So that means that these would be classified as what? Shear thickening, shear thinning, Bingham plastic, Newtonian.
Plastic.
Yeah, plastic. So somehow we've come up with a shear, or a non-Newtonian Bingham plastic-like mixture of oil and paint. And the reason that I did this is because I wanted to target a certain speed at which these dots would begin to shear. So if I continue now, we hit that critical speed, and if you keep watching it, you start to see them smear out in the direction of the local shear stress. And so this is a way, pardon the camera, it's kind of going all over the place. That's what happens when you tie a GoPro to the end of a stick. And so what you're left with is this visualization of, since it was a nominally steady flow, streamlines, streak lines, path lines, all the same thing. The idea being is that as water flows by, it's trying to drag the paint with it. And so it creates visualizations of streamlines. We're going to come up a little bit short on time, I think. So we may not quite get to surface tension or the continuum hypothesis today, but I'll pick those up in the video lectures next week. So what we'll try to get through right now is how to compute some example computations of shear stress. So if we've got between two fixed walls, this could be the inside of a pipe. In fact, this is a classic kind of problem called Couette flow, or Poiseuille flow, I don't quite remember which. And we've got some, pressure gradient over here. Something's driving flow through it, this pipe. Then we're going to get a velocity distribution that looks like this. And we may get to the point in this course where we actually we determine the shape of this velocity distribution and we come up with this value mathematically. But if this is the distribution of velocity as a function of y is equal to 3u over 2 1 minus y over h squared. And u is the average, the mean velocity flow. So if we integrate the entire mass flow rate divided by the height of the fluid here, we're going to get an average value, which is u. All right. So now, let's go ahead and compute. So let's draw this as the center line. Okay, so we already derived that that tau yx is equal to, and anywhere in the fluid, mu times du dy. So if we want to compute the shear stress at this point and at this point, the first step is going to be, if this is u, taking its derivative with respect to y. So you guys get to put on your calculus hats and give me a derivative. I have it written down, so I'm going to know if you read it wrong, but anybody? Anyone got a expression for the derivative with respect to y? All right. For the sake of time, is equal to 3u, big U, y over h squared, negative 3u y over h squared. So to compute the shearing stress at these 2 points, we have to plug in these respective values of y into this equation. So tau yz at y equals 0, this is at the wall, is going to be what? If we plug 0 in here, this is not, oh sorry, 0 is along the center line, that's right, because yx. 0 is along the center line. So we plug in 0 here, right? We get 0. That's because if we take the tangent line here, the velocity is not changing. The slope of the velocity is 0 along the center line. So there's no relative motion between layers of fluid, therefore no shear stress is developed. Tau yz at y equals negative h. That's this point here. It's going to be equal to, if we plug in negative h, what do we get? Remember, mu times du by dt, evaluated at negative h. So I'll go ahead and put the mu in there.